This is the last of the 4 sessions about type functional programming in Haskell, and in it we're going to cover 2 fairly different topics, namely those of type inference and of input-output in Haskell. So, as I've just said, there are some very distinct learning goals for this session. The first learning goal is that after this session you should be able to understand the Hindley-Milner-Damas type inference algorithm for parametric polymorphism. And the second is that you should be able to understand and use input-output in Haskell. First, let's look at type inference in Haskell. One of the very nice features of Haskell is that type inference is possible in a very nice sense. The type system satisfies the property of sounding complete type inference. What I mean by that is there exists an algorithm that will take any expression E and attempt to compute a type of E, and moreover, the algorithm will find a type T if and only if E can be typed, and the T that will be found is the most general type that E can have in the type system for Haskell. So that's a very powerful and very useful result. We've seen that there are actually 2 kinds of polymorphism at play in Haskell. One called parametric polymorphism, that's the one that we capture by the Hindley-Milner-Damas type system. That was the subject of the previous session. And the other notion of polymorphism we also saw in the previous session, and that's the notion of ad hoc polymorphism. And in Haskell we capture that by means of type classes. Today's session we'll look at how type inference is handled for parametric polymorphism. So we're not going to look at ad hoc polymorphism, but I will return to it very briefly at the end. That we can actually do type inference for parametric polymorphism, that's a very deep result in computer science. Dates back to 1977, and it's used in other settings than that of Haskell. For instance, in the languages of the ML family and in other type functional programming languages, this same result is also extremely useful. So this is more than Haskell. This is a very general result in computer science. First, let's look at the type system again, just to recap. This was the type system for an applied lambda calculus with expressions and constants. And the expressions that we have are the expressions of the lambda calculus. We have variables, we have abstraction, we have application, and then moreover we've got pairs, and we've got let expressions, and we've put constants. And the constants that we have are enough to represent the natural numbers and truth values, and we also have a test for 0. So 0 is a constant. For any expression we can form the successor, and because of these 2 constants we can represent the natural numbers. We have the truth values, true and false, and we have the test for 0. Now the types in the Hindley-Milner-Damas type system are given by the formation rules that we have here. We've got types, we've got type schemes, and in a type we can have type variables. And type variables are quantified over in the type scheme. A type scheme is a polymorphic type. It says that for all types A, we have T. And the types that we have in this version of the system are enough to capture what we can talk about in the language. We can speak of pairs, so we need to have a pair type. We have functions, so we need to have a function type. We have natural numbers, we have an int type, and we have truth values, so we have a bool type. So that's what we have in the Hindley-Milner-Damas type system that we saw last time around. Our algorithm for type inference is called the W algorithm for well-typedness. It's a recursive algorithm. It's really a recursive function, and it's going to try to construct a type derivation tree by applying the type rules in a bottom-up fashion. And every case in the body of this algorithm corresponds to one of the type rules, as we're going to see in a moment. In the algorithm, we use type variables to represent the unknown types that we must find. And we see the expression that we're going to type as type with unknown types, and then in the process we find those unknown types. Sub-expressions have unknown types that we must find. To be concrete, here's an example of an expression. Let f equal lambda x, lambda g, g of x in f of naught applied to is 0. F is typed with a1, an unknown type. The lambda here is typed with a2, the g here is typed with an a3, and the entire expression is typed with an a4. And here, what we're trying to find are precisely a1, a2, a3, and a4. So all the bound variables in our expression are annotated with these unknown types, and the entire expression is annotated with a type. So eventually, if the algorithm succeeds, it's going to give us a substitution sigma that for every unknown, meaning for every type variable, assigns a type. Now, substitutions are just functions, and so type substitutions can be composed because they're functions. If we have two type substitutions, sigma 1 and sigma 2, then sigma 1 circles sigma 2 is also a type substitution. It's given by the composed substitution applied to a type variable is found by simply applying sigma 2 to A and then applying sigma 1 to the result. And we can speak of one substitution being more general than another. If we have two substitutions, sigma and tau, we say that sigma is more general than tau if we can find some intermediate substitution, sigma prime, that will allow us to express tau as sigma prime composed with sigma. So that's what it means to be a more general substitution, and the most general substitution is one such that no other substitution is more general than it. So more precisely, a type substitution is a function sigma from type variables to types, and it's a partial function because it only gives us the types for the type variables that we actually mention in our expression, not every type variable under the sun, only the ones that are relevant. And if we have a type expression t with type variables in it, then sigma of t is the type expression we get by applying sigma to the type variables in t. We replace every type variable by the value found by sigma. And the identity substitution, that's the very boring type substitution that simply substitutes A by itself. Sometimes we're going to talk about this and we call it id for identity. Sometimes in this algorithm we're also going to solve equations over type expressions. For instance, when we try to find the type of an application E1, E2, where E1 has some type T1 and E2 has some T2 that we're trying to find, then we must have that E has a function type T2 to T. And we want T1, which is the argument type, to be T1 to T. So we're trying to find a T and T2 and T1 so that this equation holds. And this really means finding a type substitution such that if we apply the substitution on the left-hand side and we apply the substitution on the right-hand side, we get the same type. And the substitution, which has this nice property, we will call a unifier. Can we find such a unifier? Yes. First, let's look at a couple of examples. First, here's an equation. A to int, where A is a type variable, should be bool to B. Can we find an assignment to A and to B such that this equation holds? Yes. Let A be bool and let B be int. So the unifier is this substitution. Sometimes we cannot find a unifier. For instance, if we have this equation, the product type A times int should be bool to B. It cannot have a unifier because a product type cannot also be a function type. So there is no unifier here. There is an algorithm that will always find a unifier, and it's called a unification algorithm. This is a standard algorithm, and it's used in many areas of computer science. And here it is. It's a very simple algorithm that's defined by a collection of clauses. If we want to unify a type variable with t, then all we need to do is to set A to T, so we return the substitution A to T. This only makes sense if A does not occur here. We need to check that A does not occur in T. This occurrence check is important because if A occurred in T, we would never finish substituting A by any substitution. So this occurrence check is needed. What if we want to unify two function types, T1 to T2 and T3 to T4? Well, first T1 and T3 must be unified. We need to find a substitution that will equate T1 and T3, so we call unify. With T1 and T3 we get a substitution, and then we apply the substitution that we now know to T2 and to T4, and then we call unify again. We do the same with product types. We first try to unify T1 and T3, and then if that works out okay, we try to unify T2 with sigma applied and T4 with sigma applied. If we have T and T, they're easily unified by the identity substitution. If none of these cases apply, we cannot unify, so we fail. So note that in this clause and in this clause, we're saying that if this works out fine, if this does not fail, we continue. Otherwise, we fail. So that's the unification algorithm. We can now prove a very nice result, which is that if we have a unifier for two types S and T, then we can find the most general unifier for S and T, and it can be found by running the unifier algorithm with parameters T1 and T2